let's begin. Welcome again. Last time we got started slow and easy. We're going to step on it a little bit. Today I hope to finish chapter 1, which was posted on Canvas. So some of you didn't find the textbook at the bookstore. Apparently they sold out. So I posted chapter 1. I found a PDF of it, so I posted it on Canvas. It's not very good resolution, but it does the job. You can select text and copy it and edit it. Please use it fairly. Keep it, don't sell it or anything. Keep it within the fair use policy, which allows you to use it for educational and personal purposes. So we're allowed to do that. So you can take your time to find a good, cheap copy of the textbook. The slides have been posted as well, and the first YouTube the lecture has been posted as well. And for those just coming in, we have a quiz. Please get to it on Canvas. And try to come in on time. Next time, if there's something that keeps you late, let me know, and we'll figure something out in terms of the timing for the quiz, okay? We will start with definitions. Chapter 1 is very kind of easy. Chapters 1 through 3 are pretty much lightweight. It's some stuff that you've already known, but or maybe not. So we'll go through them anyway and reinforce these concepts. If it's the first time you've heard these concepts, then that's great. Some of these concepts, I've heard of them for the first time, actually, so it was a good learning opportunity for me. Again, this is going to be very dense in text, which is unusual for my lectures. But the first time I teach a course, as I build the lectures, I start like this, and then I start refining over time. So, you know, that's the price you have to pay for being the first time taking statistics with Professor Saad. So we'll start with some definitions. The first definition we will deal with is what a population is. A population is defined as all the people or things that you are looking at. So remember what I said last time, statistics is a very attractive topic when it relates to like epidemiology and people and disease, right? So most of the time, the subjects or the people you are doing statistics on, the things you're doing statistics on are people. So that's, we call it population. But you can do statistics on things in engineering, like in product design, for example, in process design. You would be doing statistics on things or chemicals, etc. So a population would include that as well. Now, a population doesn't mean the entire world. I could be, this class could be my population, okay? Like, what if I'm collecting a certain statistic or certain information about the students who take statistics in chemical engineering, then you are the population, that's it. Or if we're doing, we're collecting data on programming knowledge for students in engineering, then students in the College of Engineering are the population at the University of Utah, for example, or across the nation. So a population doesn't mean all the entire world. That doesn't make sense. You define what the population is, and then you work with that population to see how you can develop statistics on it. A parameter is a numerical description of a property or a variable that you're trying to understand for a given population. And so, for example, the average height of students in engineering, the height of students in engineering, okay? That is a parameter for all students in engineering, okay? Or it could be the age, for example, or it could be hair color, okay? Now, on the opposite side, we have a sample, and a sample is only a representative portion of a population. Why do we need the concept of a sample? Because oftentimes populations are large to track. You cannot survey large populations. It's expensive, unfeasible sometimes. And most of the time, these populations are large groups, like engineering students across the entire nation or across the world. You can't just go and survey everyone. So you have to pick a representative sample. Now, by definition, a sample in statistics should be representative of the population. So it should try to reproduce the properties of the population, like ratios of women and men and ethnicities, etc., or whatever is important for that study. Like if it's a medical study where sensitivity of the medical thing that you're studying depends on ethnicity, for example, then ethnicity is very important in that case, and your sample needs to reproduce that correctly, okay? A statistic, so now compare sample to population. and compare a statistic to a parameter. Okay, a statistic is the same, it measures the same variable of interest, but for a sample. So when you say the average height of students in the College of Engineering, okay, that's a parameter where the population is the College of Engineering students, versus the average height of students sampled from the different departments in the College of Engineering, like we sample 100 students versus the 5,000 students in the College of Engineering. The height of the students, the 100 students in the sample, is called a statistic. Okay? Compare population parameter and sample and statistic. If you remember in numerical methods, when I talked about the standard deviation, and I said there was a difference in the formula in the standard deviation for the population versus the sample, where you had in the denominator, we had n or n minus 1, if you remember that. In that case, the standard deviation for the sample is a statistic. The standard deviation of the population is a parameter of the population. Okay? A variable is something that you're trying to measure and that changes for different members of the population and the sample, of course. And that's what you're trying to track, collect statistics on. Data is the information that you've collected for a specific variable in the population. So that's the information you tabulate, you put in spreadsheets or CSV files, etc. A census is when data is studied for each and every member of the population. Okay? So if you are able, so for example, if my population is this class, I can survey all of you. It's easy, there's 55 of you, doesn't take much time. I would call that a census. Now, I probably cannot draw any conclusions outside this population, but for this population, yeah, I can just go and survey everyone and it'll be just fine. Okay? So we call that a census. Okay, let's do some examples. A consumer advocacy group wants to survey residents in the Midwest regarding hospital care. The group mails out 11,450 surveys, surveys to randomly selected households in the Midwest. A total of 942 surveys are completed and returned. Okay, so they mailed out 12,000 surveys, only 942 responded. Out of this group, 57% said that their hospital care was above average. Okay, so they took this data, they took these surveys, 942 of them, and 57% of the people said that their hospital care was above average. Now, they did some analysis, and then the consumer advocacy group made a prediction and said that 60% of people in the Midwest are satisfied with their hospital care in the region. Okay, so let's answer these questions. What's the population over here? Residents of the Midwest. What's the sample? Pardon me? 942. Not 11,450, because as far as the researchers are concerned, only 942 participated in the study. So it's the 942 people from the Midwest randomly selected or the sample. What's a parameter in this case? What's the parameter in this case? Remember, parameter is the number related to the population. The statistic is the number related to the sample. So our variable of interest here is the level of hospital care. Agreed? So what's the parameter in this case? 60%. So we say that because it relates to the population, so that will be a parameter. What's the statistic? 57%. Now that's interesting. For the sample, the average hospital care was reported slightly lower than what the population is. But that's what statistical inference did to us here. We compared the result of the variable from the sample, and we figured out, make a prediction on the entire population, and we got an improvement, a slight improvement in hospital care. So once we get to inference, we will learn how to go from the sample to the population. Okay? Here's another one. In a survey, 257 residential college students at the University of Utah. So residential students essentially means students who come in person, not necessarily residents on campus, so students who come on in person. They were asked if they had eaten lunch at the union. 72% of the students surveyed said yes. After analyzing the results, it was determined that approximately 70% of residential students have eaten lunch at the union. Okay, what's the population? Pardon me? The students, which students? Residential students, not all students at the U. Only students who come in person. Okay, residential students, that's the population. What's the sample? The 257, group of 257. What's the parameter? 70%. 70% of residential students. So that's the prediction on the population. What's the statistic? 72%, right? So what was it? 72% of the students surveyed. So that should tell you. Students surveyed means that's the sample, 72% connected to the sample. That is just its statistic, okay? There's a couple more examples. I think it's kind of become obvious what we're doing here. Okay, maybe we just skip this one, okay, and the example 4. So those examples, some of these examples are in the textbook, and there's more examples in the textbook as well. Okay, now I talked about this last time, and when I discussed the difference between descriptive statistics and inferential statistics, or inference or statistical inference. And the idea is that statistical inference takes the results from the sample and makes a generalization for the population. We're going to hit that at the end of the as we move on through the course. But initially, we're going to start with descriptive statistics, where we collect data, we summarize it, we're just reporting numbers. And so essentially, those are just generally related to the sample, not the population. Okay? For descriptive statistics, if you're just collecting numbers on a sample, you're just doing that. You cannot generalize anything about the population because you're not doing inferential statistics. You make plots, etc., and that's all good. Inferential statistics is you use the data that's gathered to make predictions about the population. Okay? So you need to be able to distinguish between the two as you read sensational news stories, editorialized news stories. Be skeptical. I am skeptical of everything I read on the internet, whether I agree with it or disagree with it, especially the stuff that I agree with. I'm like very skeptical because you can twist things in so many ways, and oftentimes people don't recognize the distinction between a sample and a population, and most of the time you see things being reported on a sample rather than a population, and you cannot generalize just from the sample. Okay, so here's an example. A consumer advocacy group wants to serve. That's the same example. The residents of the Midwest and their hospital care. So remember, they had 942 surveys are completed and returned. So that was our sample. Out of this group, 57% say that their hospital care was above average. And then it was determined that 60% of the population in the Midwest, that is, are satisfied with their hospital care. So which of these numbers is a descriptive statistic and which is an inferential statistic? Yep. 57 is descriptive, obvious, right? 57 is descriptive because it's just reporting some value we calculated from the sample. So I collect information from the sample and just take an average or do an integral or something, and that's it. I'm just reporting a number. It's descriptive. I'm describing the sample. Now, when I make a prediction on the population, that becomes an inferential analysis. It's a number that didn't exist before I made the inference. All right. Next, we go to classifying data. Again, you might have seen this. This might be just kind of boring, etc., but we have to cover our tracks, right? Because that becomes important as we use precise language to communicate. In science and engineering, we need to be precise. We need to communicate clearly so that we can understand disagreements or miscommunications. We need to be clear about all the words we use. There's generally two types of variables, as you know, qualitative and quantitative variables. Qualitative variables, they describe things based on a category or on a name. Now, you can, like the month of the year, January, February, etc. Those are just random names, right? Now, you could assign them a number. So month 1 is January, month 2 is February, right, etc. But that's just an index. It doesn't make sense to take the average month of the year. It's meaningless. You cannot take an average of qualitative data, or you cannot take their differences. You know, it's just arbitrary, right? Now, typically we assign an index to these things, right? But they're not necessarily computational in nature. So it's harder to work with qualitative data because they're categorical, they're based on names and labels. So it's hard to do computations with them. So we have to be careful when we do statistics on qualitative data. On the flip side, there's a quantitative variable is a variable in which the numbers act as actual numerical values. So although you can use numbers to describe qualitative variables like the month of the year, right? That number doesn't act as a numerical value. It just acts as an index, okay? A quantitative variable is a number that acts as a numerical value. So like the temperature, your temperature, you know, when you were sick, right? So that's a number that you can measure, you can do things with, you can compare numbers with other numbers and so on. So that's a quantitative variable. Some examples here, number of siblings, property evaluation, etc. All right, so here's a table listing these variables: age, gender, race, salary, month of the year, and medicine dosage. And I want you to identify whether it's a qualitative or a quantitative variable. So age, quantitative, okay? Gender, race, qualitative, salary, okay, because, and then you can compare. You can say, oh, this person gets paid twice as the other person, right? The months of the year, qualitative, right? Even if you're using a numerical value for it. And medicine dosage, quantitative. Okay, good. All right. So there's some other examples here, like shades of green, rankings of the most popular paint colors, amount of blue. It's quantitative. So a bunch of examples, you can go through them. These are, some of them are lifted directly from the textbook. Now, there's also more variations on between qualitative and quantitative. Now, in quantitative variables, there's two types of data. There's discrete data and continuous data. Discrete data takes on only specific value and typically is just a count, like the number of students in this class. I cannot have 55.23 students or 7 square root of 2 students. Doesn't make sense. Although you might see on average, like the fertility rate in the US is 2.1 children per woman. Well, you know, what that means is for every 100 women, you have 21 children, right? So that's how I would think about it. Or for every 10 women, there's 21 children, right? So, but 2.1 children doesn't make sense. So the number of children, the number of students, these are discrete values. Continuous data is data that changes continuously on the scale, like temperature, volume, flow rates, etc. Okay? Now determine the following, if the following continuous or discrete. Temperature in Fahrenheit, continuous. Number of houses in the city. You can't have 700.3 homes, right? You have either 700 or 701 homes. Unless a home is like really, really in bad shape, it's considered half a home, I guess. Numbers of elliptical machines in the YMCA in Utah. I don't know, come up with that example. I hope do they have any? I hope they have some. Heights of doors, so this would be discrete. Heights of door is continuous because this door is, you know, you can measure it to a certain precision and you can measure another door, they compare them, they're continuous variables. All right. Next is levels of measurement, and that one was interesting for me because I used to use the word nominal value as to refer to the number, to a number. When they tell me, oh, you know, this year the number of students dropping from class has risen 200%. Like 200%, that's a lot. What's the nominal value? What's the numerical value? Oh, it went from 1 student to 3 students, right? Or 2 students. That's not much, okay? But I used to use the word nominal in that sense. It means something different, actually. So we start with a nominal variable. Now, the word nominal comes from nom in French or nomina in Latin, I think. And it means it's a label. So nominal variables come from the word name, and these are things that you name, like months of the year, right? January, February. So it's qualitative data that consists of categories and labels. There's no meaningful ranking in nominal values, and you cannot do arithmetic operations in them. You cannot subtract them. You cannot add them. You cannot divide them. You cannot compare them in any meaningful way. Okay? They're just completely arbitrary, but they're names. Okay? So for example, eye color, blue, green, brown. You know, these are just nominal variables. There's no specific ranking. You can choose to rank them by alphabetical, you know, by the alphabet or by their first letter. It's fine, but there's no intrinsic meaning in terms of magnitude or signifying which one is stronger or lower or higher than the other. Types of cars, sedan, they're just cars. SUVs, they're just arbitrary names for these. Brands of laptops, like, you know, Dell, Apple, HP, etc. So these are nominal variables. Okay, they're just categories. The next level of measurement is called ordinal, and that comes from the word order. So nominal, name, it's a label. Ordinal comes from order. So it's an ordinal variable is a nominal variable that can be ranked. Okay, so it has a name, but you can rank it in a certain order. Okay, so it's a qualitative data that can be arranged in meaningful order, but still you cannot do any calculations on them. So differences between data points are not meaningful. But the ordering must make sense. Okay, it must proceed in a certain order. Like education level, you start elementary, middle, high school, bachelor, master's, PhD. That's a natural order. I didn't make that up. Right? It is a natural order that falls into place. But all of these variables they have labels on them, so they're ordered nominal variables. We call them ordinal. Customer satisfaction ratings, very dissatisfied, and so on. Or like that scale, you go at the doctor and they put you on a scale from, you know, 1 to 10, how much in pain you are. Movie ratings, 1 star, 2 star, 3 stars, etc. Okay, so these are ordinal variables. The next one, so we were dealing with qualitative, so there's 2 levels of measurement for qualitative variables, and there's 2 for quantitative, and this one is interesting. An interval type variable, who's heard of that designation before? Me neither. It's like the first one I hear of it, but it's very useful, and I get it why it's very useful, and there's a trick question that I will ask you about that. So an interval quantity is a quantitative variable. So you can measure it continuously, etc. You can measure it, you can get a value of it, but it does not have a true zero. It does not have a true zero. So, for example, temperature in Celsius or Fahrenheit, 0 degrees Celsius doesn't mean no temperature. Now, if you're baffled by that, wait until you hit heat transfer to understand it. But at 0 degrees Celsius, it doesn't mean there's no energy in the system. It's just an arbitrary point that was chosen to say, oh, water freezes at sea level at 0 degrees. We're going to use that as our reference. Okay, but 0 degrees, the system still has energy in it, still has thermal energy. You can go negative, you can go positive. But that 0 is not like a true 0. Calendar years, for example. The year 0 doesn't designate no years existed. Okay, it's just an arbitrary point where we started counting years. Time, if we want to measure true time, where time started, we got to go 13.531 billion years. So today would be 13.5 billion, however many thousands you want to count that, right? But in our calendar system, there's no year 0 in the sense 0 doesn't mean no years at all. Okay? Now, here's my question. Temperature in Kelvin. Does that have a true 0 or not? Does it? So let me say this first. Okay, temperature in Celsius, you can say that the difference between 30 degrees and 20 degrees is 10 degrees higher. Or you could say 40 degrees Celsius versus 20 degrees Celsius. But can you say that at 40 degrees I'm twice as warm as 20 degrees? Okay, in Kelvin, can you say 40 degrees Kelvin is twice as warm as 20 degree Kelvin? Yes. Why? Because Kelvin has a true zero. The absolute zero is a state where there's absolutely no thermal energy in the system whatsoever. That's why engineers and scientists like to use the Kelvin scale, because it's the true scale of the universe, and it does have a true zero in it. And therefore, you can say that a system at 40 Kelvin is twice as hot as a system at 20 Kelvin. But you cannot say that on a system with Celsius or Fahrenheit. Okay? Which takes us to the final level of quantitative measurement, and that's called ratio. I don't know why they came up with these names, interval and ratio. But ratio is an interval quantity, a quantitative variable that you can measure, but it has a true zero in it. It has a true zero. Like the Kelvin scale, height, 180 centimeters is twice as tall as someone who's 90 centimeters. The way you remember the difference between the two, think of the example of 40 degrees Celsius and 20 degrees Celsius. Can you take their ratio? No, it's meaningless. 40 degrees is not twice as hot as 20 degrees, although their ratio is 2. So there's no true ratio in interval data. Okay? In ratio data, that's why they call it ratio. You can take the ratio and you can say, yes, this is twice as much or this is 3 times as much. Okay? So 180 centimeters is twice as tall as 90. 20 kilograms is twice as heavy as 10 kilograms. Why? Because the weight has 0 kilogram means no mass. It has a true zero in it. Okay? Income, 0 degrees means, you're making no money. There's no money in the bank. $0. Sorry. $20,000 is twice as much as $10,000. Okay, so you can take that. So remember the word ratio. You can take their ratios. Think about the Kelvin example. Yeah, I can take the ratio or the height of the person. Okay? Put this nice table for you here. Okay, to summarize this. With the help of ChatGPT, actually. So make a table for me with these data, and it helped me. But then I had to edit it here in Keynote. And then I made this for you as well. And to try to summarize kind of where we rank. So given type of data, you have qualitative and quantitative. For qualitative, you have nominal and ordinal. And for quantitative, you have interval and ratio. Okay, so you can figure out where you're at. Let's do some examples with this. So we start with this one. The finishing times for runners in a 5K race. So I'll do this example with you. So the finishing time, what type of data? Is it qualitative or quantitative? It is a quantitative data, right? It is a quantitative data, so we are here. Okay, can be arranged in meaningful order, but 0 doesn't matter here. Here 0 matters, so yes, 0 matters here. If you finish in 0 time, then you're faster than Usain Bolt, the fastest person on earth, right? So 0 does true exist. A true 0 does exist for a finishing time, right? So we are here, and therefore this data is a ratio type of data, okay? Okay, let's do this one. Colors contained in a box of crayons or markers. Nominal. Okay, it's nominal. So it is qualitative. It has a name and label, but doesn't have a specific order. So you can't say, oh, red must come before green or green. No, doesn't. It's an arbitrary decision, right? So it is just a nominal type of variable. Boiling points for various liquids measured in Celsius, not in Kelvin. Okay, so it's a quantitative variable, but doesn't have a true 0. Because Celsius doesn't have a true 0, neither does Fahrenheit. Okay? So now go and mess with your senior colleagues at the ICC. Tell them, is a system at 20 Celsius twice as hot as a system at 10 Celsius? Okay? Go and ask them that question. Seriously. Okay. Interval. And then finally, the top 10 summer vacation destinations. It's ordinal because you're ordering them by, top destination. Okay? So 1, 2, 3, etc. All right. Next, we go on to statistical studies. So we're almost wrapping up with chapter 1. And what is a statistical study? A study that does statistics on something, obviously. But in practice, we can't take a census of every member of the population. We cannot do a census. So we have to gather a small number of people that is manageable, that we can track and measure quantities on, right? Survey them, potentially administer a fix. Now, in engineering, what that means is, say you have something in your product design, an issue in quality control, right? And then you go and propose, you want to analyze what's going on. You collect a sample from your products. It could be, you're making, my friend graduated from here, chemical engineering. He runs the research group at US Gypsum. So they make about 60% of the drywall in the entire world. Okay, so, and he leads the research division. And sometimes they need to randomly sample and figure out kind of the properties of their drywall, right? So they need to do a statistical study to see measure the properties of their drywall. They cannot obviously test and break each and every drywall, because then they won't have a functioning drywall, right? So, they're going to figure out a way to collect some of these drywall. And then they would have to ask a question, like, what are we trying to answer? One question could be, how long could my drywall, I don't know why I picked the drywall example, I looked at the wall and it inspired me. So that's what inspired me today on the quiz. So the question could be, how long could this wall withstand a fire, at a certain level, right? There's fires raging in Los Angeles, sadly, and so, those are types of questions that you might want to ask. What is the population? It's the population of drywall, all the drywalls in the US, right? Or all the US gypsum drywalls in the United States, right? So that would be the population. What variables are we going to record? Maybe the thickness of the drywall, the type of material we used in these drywalls or the other drywalls, their heights, does it matter? The temperature on either side of the drywall, and so on and so forth, right? So those are things that you want to measure. And then, as you collect the data, then you want to make an inference on it later. Two important questions here is, what is the sampling method? How are we going to sample these drywalls? Should we take one off the assembly line every 10th drywall of the assembly line? Or should we get them all down the assembly line and just go randomly, pick one from each batch? Or should we or they are separated into batches? Should we randomly pick 3 batches and test all of those? Or pick one from each batch, right? So there's different sampling methods. And then, is this going to be an observational study or an experiment? Okay, just a little kind of wet your beak a little bit. An observational study is something that you collect on something that's already existing. So tracking people, tracking drywalls that have already been installed, okay, or that have already been produced. We're not interfering with the system. We're only observing what already exists. An experiment is an intentional observation that includes a treatment. Okay, so in an experiment, we would be asking a more important question, and that would be, if we add this aluminum particles in the drywall, does that improve the heat transfer characteristics of the wall? So we have to apply a treatment. The treatment would be adding aluminum particles, and then we would analyze the system, okay? Then we collect the data, organize the data, and analyze the data to answer the question. So these last 3 are going to be left for the rest of the semester. Today we're going to try to cover these questions here. Okay. So here's an example. Best way is just start with an example. Let's imagine we want to understand the significance of walking to reduce heart attacks. The goal of the study is to determine if walking 30 minutes a day will reduce the occurrence of heart attacks. So what question we're trying to answer? So we're not designing studies yet. I mean, hopefully by the end of the course you have an idea of how to design a study. But now we're just kind of learning how studies are done, and we start with some examples. So what question is this study trying to answer? Does walking 30 minutes? Yes, Aaron? Does walking for 30 minutes reduce heart attacks or not? Okay, what is the population? Could be everyone, or probably those who are at risk of heart attacks, at higher risk, or everyone in the population, right? What variables are we recording? Yep. How many minutes or number of steps, right? And whether the person had a heart attack or not, right? So we're going to track we're going to track the people that we attach like smartwatches or something, and then track them and see if they end up having a heart attack or not in 3 years or 2 years. Okay. All right. Next one. Urologists want to study the effect of vitamin C on nerve disorders. I know these examples sound banal and simple, but there's still knowledge in them, okay? Things that you'll learn, because we can trip you up in just by complicating the question just a little bit. Neurologists want to study the effect of vitamin C on nerve disorders. The goal of the study is to see if taking an intravenous dose of vitamin C will reduce the amount of nerve pain reported by patients. So they go to the clinic, we inject them with vitamin C, and see what happens, okay? So what question we're trying to answer here, or this study is trying to answer? Mm-hmm. And yep, what is the population?
Those just with nerve disorders?
Yep, those with nerve disorders and who report nerve pain. So what variables are we recording? Exactly, yep. So we're reporting dose level of vitamin C, see if there's a relation or causative effect there, and how much pain or the nerve disorder incidence or the nerve pain incidence. Okay, now let's dig in a little bit deeper into observational versus experimental studies. So in an observational study, like I said, we use the data that's already available. So that's retroactive data. So for example, we could go to a clinic and ask a question: how many people have taken the flu shot this year, or the COVID vaccine, right? And try to gather whatever data is available. So that's called a retroactive observational study. Or you could do a proactive study, but you're not interfering in the population. A proactive study would be go hang out at a clinic and just report everyone who's coming in to take a flu shot or a COVID vaccine. You're not telling people to go and do it. You're just observing. You're not interfering, okay? I always think about those like reporters who go on wild safaris, or the reporting like in locations of war, and they don't interfere. It's like I can't do that. Like if you're seeing, like sometimes you see it takes tremendous effort to restrain, right? Not to interfere. If like there's like 2 lions eating something, and I don't know. Anyway, so you have to be very you cannot interfere in the observation, okay? You cannot, and the problem with observational studies is you cannot definitely determine cause and effect. You can only look at correlation. Okay, there's this website, I forgot the name, but you can find correlation between anything in statistics, got a ton of data, and you can plot anything versus anything else. I'll look it up and I'll send it to you. Maybe we do an example next time in class. Its limitations include finding quality data for a retroactive study and the time it takes to collect data for a proactive study. So in other words, you're not in control. You know, it might be hard to just go and see all the clinics that have administered certain vaccines and whatnot, or if you find those clinics, or actively maybe people are not motivated, they're not doing this year, right? So it becomes hard, you're not in control of the study. But what's nice about observational studies, like today you can go on like the global data survey and just pick any set of data and start analyzing it. There's a lot of data that's already been collected. Okay, so that's kind of the advantage of an observational study. It's really cheap. All you have to do is just go and grab the data. It already exists. An experiment, on the other hand, is you apply a treatment of any kind to determine a cause and effect relation, and that's very, very important. So typically, in medicine, this means applying that's why we call it treatment, because you're administering something to the system, you're giving medication or doing a surgical procedure. In engineering, this could be changing the material composition, doing something to the process, and then comparing. If I do this, does this improve? If I don't do it, does it not improve it or yes? Okay. So there are pros and cons for each. In observational studies, There's no intervention. You're just observing. With experiments, you are doing an intervention. The purpose of an observation study is to identify correlations, and with experiment to establish cause and effect. You have no control over the variables in an observational study. Like, you're just observing people. Like, what if you want to isolate the effect of a certain medication with certain other confounding factors, like, maybe obesity or heart disease or cholesterol level? We have no control over that in an observational study unless you start kind of ripping the data apart, but maybe that data was not collected, right? You're just stuck with, whatever data you have. In an experiment, you control. You say, I want all people with this certain cholesterol levels, this risk of heart disease, etc., to participate in the study. So you have more control over confounding variables. You can determine cause and effect with an experiment. You cannot determine it in an observation. For example, correlation between smoking and lung cancer. That's a correlation, very strong one. But like it's unethical to go and tell people smoke and measure if they get lung cancer, right? So that's unethical. So you really can do an experiment with making people have lung cancer. But what you can experiment on is administering a medication for those who have lung cancer. Does that reduce the incidence of et cetera, et cetera? Okay. The negatives or the limitations is data quality and constraints for an observational study. For an experiment, it's up to you. It's as if you design a bad experiment, you don't keep track of all the other variables that might affect the quality of your results, then it's going to be a bad study. And that's how you would critique a study. Okay, let's see. In the following, which type of study would you conduct? Observational or experiment? Let's say you want to determine the average age of college students across the nation. Observation, yeah. You just go ask the question to all the HR departments or the admissions departments. You're not designing an experiment for this. It'd be silly to do that. The researchers wish to determine if the COVID vaccination will help prevent severe cases of COVID-19. That would be an experiment. You can do an observation, but an experiment you have more control, because then you want to make sure that it's truly the vaccine that is reducing the effects of COVID, not other factors. So you do a placebo and whatnot. We'll learn about that in a second. Okay, let's dig into observational studies. And this, what I'm going to talk about here also applies to experiments. So it doesn't necessarily fit just under observational studies. So I will change the title later. But this has to do with the type of sampling. So like I said, you cannot do a census. We cannot do a census. So a census means measuring everything for the entire population. And we'll take a break. Let me see. We'll take a break after. Actually, let's take a break now. Okay? 5 minutes. Come back, please. Okay? Hey, Zach.
The outlet right there almost caught on fire when Ashton was using it to charge his computer.
Being plugged in, it just starts smoking in the middle of the lecture.
Oh my gosh.
Yeah.
Oh, I could see it. Yeah. Uh-oh.
So yeah, like it was smoke started coming out of there, started hissing.
Wow. Yeah, my friend was just sitting. He was working on his MacBook, and the thing bulged up like this. The battery.
Was it
The battery.
to that?
No. It was not here. In like just yeah.
Battery, these bumps were there before. I think it's just with the stickers. So
I think-
that pack is fine, but I think it's more with the.
I think it's
Outlet.
this thing.
Yeah.
Because there must be some sort of short when you some fault in there.
Yeah. So no, this was smoking.
Yeah, it was this
yeah,
thing.
Yeah. Okay.
Oh.
Don't touch it. We'll report it. That's fine. Yeah. Hey, what's up, Soren?
I was going through the science, but the continuous and discrete one. Could you explain what's the difference between continuous and discrete again?
So discrete is just a it's a fixed number, like 1, 2, 3, 4, 5. That's it. You can only choose one of those values, or 1.5, 1.6, 1.8, 1.9. You just have a set of values, and the variable can only take on one of those values. But a continuous variable is something that changes continuously, right?
So like from like 1, 2, 3, 4, 5, that's discrete. But if it were continuous, like 1, 3, 2. I'm sorry, I'm trying.
1.1, 1.1, 1.156, 1.237, 1.78, 2. That's continuous. It's continuous numbers along. Continuous,
Yeah,
right?
yeah.
Discrete is only specific values. It cannot take any value in between those values.
Oh, it can't. So like say 1 and 2, discrete can only do those two numbers.
Yes.
But if it's continuous, it'd be like 1.1, 1.2, like that.
Yep.
Okay, thank you.
Yep.
Sadly, just the definitions for discrete and continuous aren't here. Slides.
Yeah. So because I updated that later, but you can find it in the textbook, so in the PDF file, right? Yeah. Yep.
And into the stats.
Yeah. Beginning stats.
Oh, beginnings.
Yeah. Chapter 1. Yep.
Oh yeah, I
Yep.
have that.
Oh, is it linking to the wrong thing? Nope, it's right. Yep.
All right, I'll make sure to take a look.
Yep.
Thank you.
I mean, yeah. You should know this. Continuous, discrete. It's
Yeah,
yeah.
Make sure I get my definitions and understanding.
All right.
Let's
see.
for that thing when you're talking about it.
Let's resume. I changed the title to sampling methods because this will be applicable to observational and experimental studies. I'll update the slides after I get back to my office. So like I said earlier, you cannot do a census. Instead, we want to collect data from a sample of the population, and a sample is a representative of the population. Now, there are different ways to design a sample and pick your constituents. And that often always depends on the type of statistic you're trying to do. And that's where good statistical intuition and experience comes into play. So I don't expect you to just know off the bat, like right now, what type of sampling methodology is going to be effective for a complicated project. For simple projects, it's kind of will be obvious, but let's go over the different types of sampling methods and see their limitations and their properties. We have about 1, 2, 3, 4, 5, 6 of them. Random sampling, simple random sampling, stratified sampling, cluster sampling, systematic sampling, convenience sampling, just to name a few. Apparently every week there's another kind of sampling methodology that comes up because they recognize, oh, this statistical study didn't produce the results that we can actually measure. We can do better by improving our sample, etc. So we start with random sampling, and by definition, in random sampling, every member in the population has an equal chance of being selected. no questions asked, nothing else is taken into consideration. It's one of the simplest types of sampling methods. So what you essentially do, you assign a number to every member in the population, give them an index, okay, and then just randomly select numbers. Let's say you are my population, okay, all of you, and for some reason I cannot do a census here. I want to pick a sample of 10 students. The size of the sample, we're going to study that later. But let's say I want a sample of 10 students. What I would do, I would just randomly assign a number for each one of you. Your number 1, 2, 3, 4, 5, 6, and so on. And then go to a random number generator and say, give me 10 numbers going from 1 to 55. It would pick 1, 17, 18, 25, etc. And then I would just send a survey to those students, because now each number, in reality, each number could be assigned an address, and then you mail something to that address, or it could be a patient in the hospital. Typically are done anonymously, and so to hide personal information. The advantage is that it minimizes bias, ensuring a fair representation of the population. It's not always practical though, especially with large populations, because you don't have a list of the entire population. For smaller populations, it's easy, but for bigger ones, you might not have every address on the book. You might have people who have moved out, who vacant homes or tenants, etc. A simple random sample is similar to random sampling, but it's a type of random sample where each possible sample of the population has an equal chance of being selected. I'll give you an example. If I want to know how on-campus students would rate the food in the cafeteria, I could randomly select several in-person classes. So I would take a bunch of samples from the population, and then randomly select several students from each sample. Okay, so I would take all the in-person classes first. Okay, so now that reduced. So let's say my population is the University of Utah students. Let's say half of you stay at work, study from home, and the other half comes in person, right? So what I would do, I would just look at the in-person classes, my samples are the classrooms, right? Because you're here in person, and I would randomly select students, one student from each classroom, from each sample, okay? So in a way, you've narrowed down your random sampling. It's a simple random sample. It's easy to understand. I disagree with that, but it's easy to understand apparently and implement with small and manageable populations. And again, it can become difficult for larger populations. Okay? I've rarely seen this simple random sample. I've seen random sampling or the other types. Now this one is interesting, stratified sampling. So the word stratification comes from strata, okay, or levels of a certain value or certain members of the population. In this case, the population is divided into subgroups called strata based on relevant characteristics: age, gender, ethnicity, hair color, whatever, right? So let's assume you're studying a certain effect that affects, you want to see the measurable effect if it affects ethnicity, for example. So you want to make sure in your sample you're representing the population correctly. Or let's say we're doing something different in our curriculum, but we have freshmen, sophomores, juniors, seniors, right? And I have, my population consists of 60% freshmen, 50%, 40% of the other categories, right? I want to make sure that my sample has a representative from each one of those groups, or stratas, we call them, okay? Now, again, it depends on the specific study and what you're after. If being freshman, sophomore, junior, senior is going to matter more than what your gender is or what your ethnicity is, then I discard those other variables, but I only focus on what category you're in, what stratum you're in, okay? This is an example on the freshmen. If freshmen make up 40% of the student body, then our sample will be comprised of 40% responses from freshmen, maybe 20% from the sophomores, et cetera, et cetera. It ensures that all subgroups are represented correctly in proportion to the population. This makes sense, right? Your population consists 60% of this, 40% of that, then your sample should consist of that as well. It requires detailed knowledge of the population, so you need to know a lot about your population anyway to be able to do that subdivision. Okay? Cluster sampling So the hardest ones are stratified sampling and cluster sampling because they're very similar. The population is divided into subgroups, just like in stratified sampling, called clusters that are similar to the population, and whole clusters are chosen at random. So this is often used in counties and voting precincts. It's more practical and cost effective. We'll see a couple of examples next. And it risks that some clusters are not representative of the population. Okay? And finally, two more. Systematic sampling, this is the easiest. In systematic sampling, you just pick the nth person or the nth object or the nth thing that in your sample. So again, going back to the drywall, I can say I'm going to pick every 10th drywall of the production line. Okay? That's it. Or every 10th person coming into the clinic. You're done. Okay? So it's a very simple kind of sampling. Systematic sampling, that's the easiest. Convenience sampling is very easy, but it's often the worst. Convenience sampling, as the name designates, is just convenient for the researcher. Like if I want to do a sample of students in engineering, I just get you as my sample. Because you're here with me, I can send you an assignment on Canvas and measure something. You would be my sample, and then I want to make a prediction on the College of Engineering. Now, this would be a horrible sample to represent the College of Engineering, but it's convenient. Right? It's quick and easy. I sampled you, love of Python programming. I'll just sample, take you as a sample, report that to the college, and then make a prediction on the College of Engineering. It's not going to be a good analysis, okay? All right, here are some examples. You want to identify which method of sampling was used. We start with the first one. A pollster surveys 50 people in each of a senator's 12 voting precincts. So this should immediately put you between either stratified or cluster sampling. Okay, probably forgot the definitions. So in this case, this is stratified sampling because the voting precincts are the strata for the senator, and we're picking just 50 random people from each strata. In cluster sampling, you would pick 6 random precincts and survey everyone in each precinct. See the difference? In the stratified sampling, we cover all the strata, but we pick randomly from each strata. In cluster sampling, we pick everyone in the cluster, but only pick a few clusters. Okay? The quality control department at a cereal manufacturer measures the weight of every 10th box of the assembly line. Sorry, I'm laughing a little bit because there's a dad joke I do with my son. He loves eating cereal. And I tell him, this is horrible for you. Like, you're not getting any other nutrition, like for breakfast, lunch, and dinner if he had the chance. Like buying boxes of Kellogg's, or like then went to generic, and now I want something even cheaper. So I told him, like, you're a cereal eater. So anyway, it's a cereal, S-E-R-I-A. Anyway, it's a daddy joke. Hey, pun jokes are good, are important, like I told you, for foreign-speaking people. So anyways, the quality, so this is easy, right? This is systematic sampling. The 10th box of the assembly line, right? A female student walks down the hall in her dorms asking students how much money they would spend in a food court, etc. It's convenient, right? These are the dorm people next to me. I'm just ask them and see how much they're paying, right? It's convenient. It's a convenient sample. Okay. An educator randomly chooses 5 of the school districts in Chicago area and asks each household in those districts how many school children are in the home. So remember, stratified or cluster. In stratified sampling, you cover all the strata, but pick a few people from each stratum. In cluster sampling, you randomly pick a few clusters, but survey everyone in the cluster. So here, the educator only picked 5 of the school districts. There might be 50 school districts. But they only picked 5, but surveyed everyone in those 5. So that would be a cluster sample, right? To determine who will win $100,000 shopping spree at the mall, the manager draws a name out of a box of entries.
I was just curious how simple random
Yeah, it's very similar. Yeah. Like I said, there's not even an example on simple random sampling. So I think it's the same as stratified sampling. It looks very similar to it. So I wouldn't sweat it. Like I haven't never seen it in any study saying we use simple random sampling, just use random sampling, right? But it's very similar. Good question. Okay. So this one would be just random sample, right? Randomly picking a name out of a box. Okay. Here's a summary of these things. So the key thing here is to recognize the difference between, these are the hardest, stratified and cluster. Stratified, a few members of each group. Cluster, each member of a few groups. Okay? So keep that in mind. All right. We have a few types of observational studies. You've heard of these words: cross-sectional study, longitudinal, meta-analysis, case study. Today we will learn what those mean. Very simple. A cross-sectional study is a study where data is collected at one point in time. So the way I like to think about it, if you think of the arrow of life moving in time, you slice a cross-section of it. You slice it at one point in time. That's a cross-section of the timeline or of the evolution of something that you're studying. Okay, that's a cross-section, one instance in time. Okay, that's a cross-sectional study. A longitudinal study is over the length of time, the longitude or the integral of time. So you track people over a long period of time. You track your product, the drywall, over 5 years, what it did and how it behaved when people were using it and throwing darts at it and whatever. Meta-analysis, it's a study that combines other studies. So like piggybacking on the research of others, right? So many people do this. They're like, okay, we'll just wait for others to spend the energy and resources to do studies on one topic, and then we're going to summarize all of those studies. It's called meta-analysis. Case study, it looks at one single event. It's not like a cross-sectional study. Cross-sectional study is looking at one variable, okay, at an instance in time. A case study is looking at a single event, many variables. The Fukushima nuclear disaster, okay? That would be a case study, right? Just one event, but looking at everything for that one event. Some examples. A group of 220 patients is followed for 15 years in order to determine the long-term health effects resulting from gastric bypass. The minute you hear long-term, longitude, okay? That's a longitudinal study, right? Okay, a gastroenterologist surveys 130 of his patients 6 months after having the surgery, gastric bypass surgery. So that's one instance in time. So, the patients had the surgery, they start the arrow of time. After 6 months, he takes a measurement. That's a cross-section. He cut the timeline. That's the cross-section in the timeline, okay? All right. Oceanographers study research on tsunamis dating from 1900 to 2000, over 100 years, to determine their effects on the ocean floor. Meta-analysis. Meta, everything. Okay? So they're summarizing the data over 100 years. Meteorologists study the Indian Ocean tsunami of December 2004 to identify warning signs. Specific event, that's a case study. Okay? Experiments are the only way to show cause and effect relationship, like we mentioned earlier. Now, with experiments, you bring in some new terminology. Treatment is some condition that, obviously, like something that you treat the patient with to see if there's an effect of the treatment. Subjects are the people. Obviously, things as well, soda cans, cereal boxes, drywall, computers, whatever. Response variable is the variable that responds to the treatment. So for example, does it reduce pain? Does it increase the heat transfer properties or heat resistive properties, right? That's your response variable. The explanatory variable is what are you changing in the experiment that could explain your response? Is it really the treatment or something else, right? So what is the explanatory variable in your experiment? Now, here's what's interesting. The control group and treatment group, you've probably heard of this, you probably know. The control group is the group that doesn't receive the treatment. Now this is, in engineering, typically, your control group is like, go back to the drywall, your control group is the drywalls without the additional treatment, which are your current drywalls that you're producing, without the additional aluminum particles or the change in the composition of the material in the drywall. But in medicine specifically, a control group is a group of subjects where no treatment is applied or they're given a placebo. The placebo effect is one of the most fascinating effects of the brain. I had a video here. I decided not to put it. Maybe I'll share it next time, about a story about this young patient who came in, and they just gave him a placebo. He was reporting pain in his arm and burning sensation from a safari. And so he came into the clinic. They apparently just gave him a placebo before they started giving him the true medicine. And brain MRIs showed like 50% reduction in pain activity. Incredible, like a measurable effect. And then they gave him the medicine that chemically does the treatment, and it reduced the pain even further. But placebo is an incredible idea, and it was discovered in like 1799, I think, by this physician who, the word placebo, do you know what the word placebo comes from? To please. So physicians wanted to please their patients. So this physician, it's like, whatever, I'll do whatever to make you happy, So to please the patient, this physician just gave her just saline. And she felt better. And he reported that in a medical journal, and that's where the term started taking over. And then later on, in the early statistics with medicine, they thought of the placebo effect as a great and very strong methodology to identify whether the treatment is really effective or not. Like if the patients who are taking a placebo do not report any improvement, but the patients who are taking the medicine report improvement, then that's a strong indicator. But if they both report improvement, then maybe that drug is not really effective beyond a placebo effect. Maybe it's just that power of suggestion that is at play here. Okay. Then the treatment group is the group of subjects who is receiving a treatment. In modern medicine and modern ethics, and for serious cases, obviously, it's unethical to just give a placebo. So then you'd have two control groups, taking a healthy group taking a placebo, or somehow they bind placebo with an old drug, but then they measure the effectiveness of an old drug versus a new drug. So now the old drug acts as the placebo. They tell them, oh yeah, this is the new drug, but it's really just the old drug, which is somewhat effective, but they want to measure kind of the improvement on that old drug. Because you don't want to, it can be unethical. Now what I did here on these slides, I have the same definitions, but with a twist on engineering. So how you would apply these to engineering. So I leave that up for you to read. Like placebo effect, there's no placebo effect on the drywall. You're not going to go tell the drywall, oh, we've given you a special material, now improve your heat transfer properties. That doesn't work that way, right? Okay. Next is single blind experiment, where the subjects do not know whether they are in the control group or the treatment group. Because if you tell them you're taking a placebo, you took away the power of suggestion, right? So they don't know if they are taking a placebo or actually taking the drug. So that's single blind experiment. But the nurses, the physicians, the researchers know who's who and who's in which category, right? A double blind experiment, nobody knows anything. Neither the researchers or the nurses nor the patients. That's very important, and that's actually the gold standard, because any slight indication, like, suppose your medicine, you have to go take it in the clinic, it's in an IV. Oh, come on in, how are you doing today? Oh, hey, come on in, you're looking good today, right? So, it could bias. The nurses, the staff, the doctor could bias if they know who's in the control group and who's in the treatment group, right? So double blind, nobody knows anything. Okay. Now, after the study, they would know. Obviously, you need to know who was in the control group, who was in the treatment group, so you can segregate and make a conclusion. Confounding variables are factors other than the treatment that could have caused an effect on the subject. And so that's very important for you to make sure if you're measuring, let's say, a treatment for heart disease, you want to make sure that anything that could contribute to heart disease, weight, cholesterol levels, genetics, etc., that those are taken into consideration. And you come in, you screen patients, and you make sure you understand what their cholesterol levels are, etc., because you want to make sure that the drug is working on the heart disease versus, cholesterol actually, a change in diet or cholesterol could have had more impact on that, right? So you gotta be careful with this. Institutional review boards, we rarely deal with this unless you're doing biomedical. Anything that has to do with human subjects, experiments on human subjects, you have to go through a review board. And finally, informed consent involves telling participants the goals and procedures involved in the study and the risks, et cetera, et cetera. This is another version with engineering focused, okay? And then finally, so once with those definitions, what you do with this to conduct the study, you randomize the control and treatment groups. So those are samples. You pick similar sampling methodologies we discussed before. Control for outside effects on the response variables. So you're bringing in, drywall example from engineering. I want to make sure that I'm taking brand new drywall that I'm working with. Or if I'm studying the heat characteristics of drywall that's been installed for 15 years, I make sure that I bring that drywall that's been installed for 15 years. Maybe it was in the sun, maybe not in the sun, maybe there's corrosion on the metal. You're looking at the integrity of metal tanks or something from explosions or leaks, right? So you bring all of that into consideration and then repeat the experiment a number of times to get meaningful patterns. So typically, other research groups start reproducing your experiment, okay? And then when a lot of those have reproduced the same experiment, a group comes and does a meta-analysis and produces an inference. Okay. All right, so here's an example, and we're going to go through it probably and then be done. We want to identify the explanatory and response variables. What's the treatment? Which group is the treatment group? Which is the control group? What's the purpose of administering saline to group B? And is this a single blind or double blind study? And what is the best choice for this study? So here's the example. Consider the study in which neurologists want to determine, taking the vitamin C example we did before, if it will reduce the amount of nerve pain reported by patients. The study was narrowed to focus only on patients with multiple sclerosis. So that's a very severe neurological disease. It causes lesions in the brain, hardening in the brain, sclerosis in the brain. So essentially hardening of the neurons. They just no more communication between the two. Just like in heart disease, sclerosis of the vessels is hardening of the vessels. They're no longer flexible. And they start narrowing down. After the study approval, the neurologists solicit volunteers who are patients with MS who are reporting nerve pain. So that's the population, right? The participants are then randomly assigned to two groups, each having 20 participants. Participants in group A are given the doses of vitamin C, and their nerve pain is tracked. Participants in group B are administered doses of saline, okay, and their pain levels are also tracked. The patients are not told to which group of the two groups they belong. However, the nurses, they know this patient is given saline, this patient is given vitamin C. And then after a predetermined length of time, the amounts of pain reported are compared to determine if the vitamin C will reduce the amount of nerve pain. Okay, so we start with the first question is identify the explanatory and the response variables. So vitamin C, response variable is pain level, okay? What is the treatment? Dose of vitamin C, right? Intravenous dose of vitamin C. Which group is the treatment group and which group is the control group? So group A, is it the treatment or control? Treatment. Group A is given vitamin C, so that's the treatment group. Group B is given the saline, so that's the control group, okay? And then what is the purpose of giving saline to group B? Why don't we give them nothing? Put them on, that's the placebo, to control for placebo effect, to give them the impression that they're getting medicine, okay? If you give them nothing, then it's like as if they don't participate in the study. is this a single blind or double blind? So single blind, right? Only the patients don't know where they are, the nurses know. And then is this the best choice? Definitely not. Always double blind studies are better, okay? So finally, I had this critiquing a study. We can cover this in 5 minutes next Tuesday. We will hit chapter 2 on Tuesday, please. Have a good weekend. Godspeed.